So now let's start with the software implementation of the FIR filter. Let's start with creating a new project. I've already created a directory on my desktop, so I'm just going to use that for my project. I'll put in a random name for the project. Just name it as FIR underscore project underscore software. And I'll have a different name for the top level design entity. Let's go to adding a device. Let's select Cyclone 2, pin count as 484, speed rate 7, select the device. I'll select model sim as the simulation tool. Now that the project has been created, I will proceed to QSys. QSys is a tool that can be used to build a complete system and then later on to interconnection between the components. Initially it will create a clock generator circuit and we can add components later on. Let's add the NEOS 2 processor. We'll use the economic version of the NEOS processor. Now let's add the on-chip memory. I'll make the total memory size at 8 KB. And let's add the JTAG module. And finally the performance counter. Once all the components are added, we'll do the interconnections, starting with the clock signal. We'll assign the clock signal to all the modules. Similarly, we'll give the reset signal. The instruction master is to be connected to the memory because it receives all the instructions from the memory, and will connect the data master to all the clocks. Once the connections are made, we'll add the interrupt. We'll now assign the base addresses, just making sure the connections are proper. We'll now assign the base addresses. This will assign base addresses to all the components. We'll now assign the reset and exception vector to the NEOS 2 processor. Now that there are 0 errors, we can proceed with the generation. This step generates the Verilog files for the different components that we have just added. I'll just name the sys file as the same as the design entity. So it generated all the files without any errors. Next step is to add all the generated Verilog files into the project. So I'll do that simply by adding the QIP file. Now that the QIP file is added, we can we can go ahead with assigning pins. Go to assignment editor. The only pin that needs to be assigned is the clock signal because it comes from outside the FPGA. We'll now add the location and IO interface. The clock is located on pin L1, so we'll add that as the value. Similarly, we'll add a standard 3.3. We'll now compile. This will create the SOF file, which we will use by the programmer. The SOF file will be used by the programmer to burn or build the project onto the FPGA board. So this is the compilation will take some time, so we can go to the NEOS2 software system. I'm just creating a new workspace. We'll add a new NEOS2 application. Here we will use the SFC file, that is the SFC information file that was just generated. We specify a project name and a project location. We select hello world small because it's the compact version of the file and it consumes less resources. We'll repeat the same steps again to avoid the error. Now to first delete the old files. Let's repeat all the same steps again. Specifying the SOPC information file, the project name and the project location. Okay, it's working now. We'll now use the programmer to burn the project onto the FPGA board. Here we'll use the SOF file that was previously created. Start the burning process. This is the auto-generated hello world small file. I'm going to replace this file with the C implementation of the FI filter that I have. Copy paste it into the file. Save and build it. Now run the system as neos to hardware. Check the output on the console. I haven't assigned the base address to the performance counter, so I'll just check what the base address is using QSys. The base address is 5000, so I'll just change the base address into the C code to be 5000 and build and run the project again. Save and build it again. And let's run it as neos to hardware. So that is the filter output, and the computation was complete in the specified time. Thank you for watching.